ants. Essentially, how it goes is we place a virtual ant at one of these towns, which then needs to pick a new town to travel to that it hasn't visited yet. The ant would prefer some place nearby, so I'll calculate each town's desirability as 1 over the distance raised to some power. The higher that power is, the more strongly the ant will prefer the nearby towns. It'll make its final decision at random, but the probabilities are weighted based on that desirability value. So let's watch our adventurous little ant on its mission. Now that it has visited every town, we can retrace its steps to see the path that it took. It's not a fantastic path, but solving the entire problem is a lot to ask of one tiny ant, so let's give it some friends to help it explore. Once they've all finished their journeys, what we'll do is score each of their paths by how good they are, and these will act like pheromone trails, as the analogy goes, to help guide the next round of ants. So ultimately, each ant chooses the next town in its path probabilistically based on the distance to the town and the strength of the pheromone trail there. In that way, each new group of ants explores random variations of the best paths found so far, and any improvements are reinforced thanks to the pheromones. Let's try run this new approach on those 20 towns from earlier to see if it actually works. I've slowed the simulation down so we can get an idea of how the pheromone trails change over time, and here it's already settled into a really good looking path. It took about 50 ants a split second to find this, which is a nice improvement from the 6 centuries we were facing before, although of course the trade-off is we have no assurance that this is actually the best possible solution. Just for fun, and please try to contain your excitement, I'm going to ramp this up to 100 towns. Here again, I am showing a slowed down view of the pheromone trails, but it's maybe interesting as well if I run it again, and instead display the best path the ants have found so far, so we can see how that develops over time as well. So I think this is a really cool algorithm. The only slightly annoying thing is there are a number of parameters for controlling the simulation, and it does take a bit of trial and error to find values that work well for a given problem. Anyway, this has got me interested in playing around with a less practical but more sort of fun visual simulation of ants. So I started by making a simple flat ant graphic and brought it to life a little with a crude walk animation. I then imported it into Unity, but something went terribly wrong in the process. And the result was mildly terrifying. I got it working in the end though, and wrote some code to make it follow this green dot around, which is going to represent the ant's food source. Here's the ant's code as it stands right now, and I want to modify this quickly to get the ant to wander about on its own. I'll try achieve this by simply nudging the desired direction by some random vector each frame, and let's see how that looks. This ant is too indecisive and not making much progress in its life, but I can turn the wander strength way down, and now it's exploring its surroundings quite nicely. I think the next step should be for the ant to be able to sense food if it's nearby and pick it up. So I've added some lines of code for handling that, and let's test this with just one ant to start with. That's working well, I think, so now I'll test this with a bunch of ants. The ants shouldn't just greedily keep all the food they find for themselves though, they need to take it back home to support the colony. I really don't know much about ants, so I did a little research about how they even find their way home. It turns out they're smarter than I'd imagined. For example, beyond recognizing landmarks, which is pretty impressive, some desert-dwelling species are apparently able to combine directional information from polarized light with distance information from essentially an internal pedometer to calculate a straight path back home. I'd like to keep things simple though, and have all navigation done via pheromones. So, inspired by this really cool video that I came across, I'm going to have the ants use two types of pheromones. This blue one they'll lay down when leaving their home to search for food, and then if they actually find food, they should turn around and follow the blue pheromones home, while laying down these red pheromones to try recruit other ants to the food source. They're not doing a great job at the moment, but that's not their fault. I haven't actually implemented the pheromone following yet. So for that, I'm going to ask each ant to sample 3 regions in front of it. And based on the concentration of pheromones it detects in these regions, it will either turn left, keep moving forwards, or turn right, plus a little bit of random turning still on top of that. I think this is a nice simple way of handling it, which I actually came across in this paper, which describes an approach to that problem we looked at the start of the video, inspired by slime molds of all things. It's quite intriguing, so I might come back to it, but for now I'll just be borrowing this little sensory scheme for the ants. Here's the actual code for it, and as you can see down here, I've made the pheromones lose strength over time to sort of mimic the effect of evaporation. I'd really like the pheromones to also diffuse outwards over time, but I'm not quite sure how to handle that yet. Anyway, let's give this a quick trial run with a handful of ants. Okay, it seems to be working roughly how I intended, so next up I want the ants to be able to avoid obstacles, or at least not simply walk right through them. So I've spent a bit of time writing some dubious collision detection code, which does nevertheless seem to be getting the job done. I then wanted to generate some sort of map like one of these from this ancient tutorial series of mine. I have a strong aversion to my old code though, so instead of reusing that project like a reasonable person, I began re-implementing it all from scratch. After several hours' work, however, I came to the realization that my new code is not so great either. Fast forwarding through some frustration, I eventually did get it working, and I also added a brush so that I could easily paint in obstacles or carve out little passageways. Come to think of it, I could have just taken 2 minutes to draw this in Paint, but anyway, I ended up making this map for the ants, and I wrote a simple spawner script to scatter some clumps of food about the place. And so, with all this set up, let's unleash 500 ants from their nest and see what they get up to. Over on the right, the ants have collected that entire food cluster, but they'll keep returning there for a while still, until the pheromone trail has finally evaporated. Real ants are vastly more sophisticated than what I'm simulating here, of course, and in this situation, for example, I read that phero ants have been found to actually deposit repellent pheromones when a resource has been depleted, to discourage future ants from that trail. This has been fun to play with, and there are many things I'd still like to try out, but my attention has been sidetracked somewhat by these strange and fascinating slime mold organisms.